I guess the first lesson of the project is do intuitive projects. That intuition is very important when you're actually designing a system. Anyway, maybe we can have a lecture on that at some point. But there are reasons why some companies are very successful in the world, right? Apple, for example. There's some intuition that goes into the design that makes it appealing to others. And having that kind of intuition as an architect is very important. It's much more important than this quantitative evaluation sometimes that we get bogged down into. And that's the kind of things that hopefully we'll get out of these lectures, that kind of trade-offs. And when you identify an idea, the ability to tell whether or not that idea is intuitively good, whether or not it will work. That kind of decision-making is very important because as you've seen in my lectures in 447 and 740, a lot of the things we're dealing with, we're designing systems that are going to be used, I don't know, 5 years, 10 years, 20 years down the road, right? So how can you actually explore the space quantitatively perfectly that far down the road? There are so many things that go into the design. Either you find a great methodology to actually figure that out because you don't know the workloads even that will feed into your systems at that point, or you come up with greatly intuitive ways of designing your system. Now, the reality is it should be a combination of both, of course. You prune the space with your intuition somehow based on your understanding that you develop, and also, of course, you explore with as best as you can with the methodology, the best methodology that you can develop. It cannot be pure intuition, it cannot be pure methodology, pure evaluation. It has to be somewhere in between. Okay. But I guess if you have great intuition, your evaluation may be terrible, and your intuition can save you. But it's usually harder the other way around. If you can have great evaluation, but zero intuition, and your evaluation, if that's wrong, and if you cannot tell that, oh, this is not intuitive, when you look at the evaluation results, you cannot say that, oh, this doesn't make sense, then you'll have a problem down the road. Okay. So before we get started, I gave you a bunch of research project topics. These are actually, many of the topics are recommended by my students, by my PhD students. And some of you actually already asked me what kind of projects should we focus on. And some of you already figured out that it might be a good idea to focus on some of the work that my students have been doing because you can get a lot of help through that. So these are projects. These will not be on the web because I do not want them distributed to the entire world. These are actually cutting-edge research topics. So if you're interested in doing some of these projects, definitely talk with some of my students. And their names and emails are here, or I can tell them who they are. I can introduce you to them. But hopefully some of these are exciting projects. And in many of these projects, the good news is the infrastructure, at least, is partially there. So you can build upon the existing infrastructure rather than starting out from scratch. That's one of the benefits. Let's see if I want to talk about any of these. Not yet, I think. So I guess I'll leave these with you so that you can look at them and figure out what you want to do, or if you want to do any of these. I would encourage you to do some of these projects, especially if you do not have a concrete idea yet. But other projects, I think they're posted on the web right now, right? Yes. So we have the project statement on the web right now. And actually, let's go there. Oh, this is some other course. So if I reload this, there you go. A new link has appeared. Oh, actually, you can. This is another thing I want to talk about. You can put your name here, update the wiki if you're looking for a project partner. And I know that some of you are. You can put your topics. If your topic is detailed, you can put your topic in detail, or you can refer to any of these topics that we have provided here we have, I think, 12 topics. And if you look at the statement here, yeah, this is updated for this semester. So proposals, we said earlier that they were due on the 21st, but I'm going to extend the deadline to 25th. Is that good for everyone? Or do you prefer more time? So 25th is, I guess, 11 days from today. So you should be able to come up with a good project proposal until then. Talk with a lot of people, I would suggest. Certainly consult with Han and me, because I'll have to approve all of the projects in the end. And certainly consult with the students who have written some of these statements, some of these project statements. Okay? And we'll be fluid in the project timeline, if you will. Milestone 1 is October 17th. And this will come very fast, so I'd encourage you to start very early. And we will talk about the way we will handle the milestone reports. Very likely it won't be reports in the sense that you won't write down a project report, but it'll be more of a presentation where you'll describe what you'll do. Okay? Any questions? And certainly the statement has, this is actually, the statement has all the logistics of the projects as well. So it tells you how to write your proposal. So it's, I'll leave you freedom in terms of the page count. It should be 2 to 3 pages. It should be well written, hopefully. That's the more important part than how long it is. And maybe Han will go over this in a discussion session sometime. And this also has the final report instructions and some suggestions if you're not going to use some of the internal infrastructures. And we also have the previous projects. You probably already looked at this document from spring 2011. Is that correct? OK. So the rest of it should be familiar to you. And some of these are still interesting projects. For example, that project 2, analysis of those workloads that use dynamic languages a lot, and design of architectures, hardware, software, co-designs that can execute those languages fast. For example, how do you execute Python fast? That's an interesting topic. If you can identify the bottlenecks in some of the code that's written in those languages, that would be useful for the future. Okay, and you can look at the papers that are referenced here. Okay. Any questions on the projects? Okay. So everybody will do a great project? It's exciting. In fact, actually, many groups in 740 and 742 have done strong projects. So I'd encourage you to strive to that. And there have been top conference publications coming out of this, both classes. OK. You remember the review assignment, right? Hopefully you guys are doing the reviews. So if you want actually feedback on your reviews, you should come and ask explicitly. I said this early on when we had the first lecture, that this will be mainly driven by students. This class will be mainly driven by students. Since it's an advanced class, you should be doing this for your own benefit. So I won't be going through each of the reviews and grading them. That's not the purpose of the reviews. The purpose of the reviews is for your benefit. But if you want explicit feedback on your reviews, you should come and talk to me or send me email. Talking to me is easier because the likelihood of getting a response is higher that way. And Han also, of course. When you send email, send it to both of us, always. OK? How many people have finished the reviews? No one? OK. OK, let's talk about multicore today. We talked about more traditional parallel processors in the last lecture. That was a very fast coverage of the entire space, if you will. entire space of 40 years or 50 years in one lecture. And I still encourage you to go and read some of those papers that I referenced, because those are carefully selected references of some of the very interesting processors of their time. And one of them is required. Hopefully you read the CM5 paper. Who has read it? There you go. Only one person? I'll encourage you to read it. That's a very good paper. Is it a good paper?
I was bored.
You were bored? That's not a good advertisement for the paper or anyone else. It's an old paper for sure. Is that why you were bored? Or?
It also kind of read like an advertisement for them.
That's right. So it's not a research style paper.
Yeah.
Certainly, that's not the purpose of the paper. Yeah, it was more, here we built this processor. Here's how it works, kind of paper. So you need to read it with the right mindset. Don't expect, and they didn't have evaluation also. For example, maybe they did actually have an evaluation, but they didn't explain it in much detail. Okay, now you can do a review of it. Okay, so you all know Moore's law. I will not cover this in detail, and this is an old chart from Intel. Basically, this shows that the number of transistors, number of devices we're able to put on a single chip is increasing exponentially. Right? And you already read this in my classes. And this is a more up-to-date chart from Wikipedia. I don't know if you can read it from the back, but this goes to 2011, and there are processors here that have more than 2 billion transistors, right? I think this is UltraSpark T3, so even this is not up to date, because there's an UltraSpark T4, right? That's bigger. Okay, anyway, the point is we have all these transistors. The question is, what do we do with them, right? And the industry's answer has overwhelmingly been, recently at least, put more processors on the same die. Right? You have all these transistors. How are you going to use them? Well, put multiple processors on the same die. That's the idea of multicore. But I guess first I would like to, in this lecture, I would like to question this, if you will. Is this a good thing to do? What else can you do with all of these transistors, all these 10 billion transistors, I'll call them, on the same die? Like, why do you have to replicate these processors? Any other alternatives? Putting more cache. That's a good one. We'll look into that. Having real large vector units, that's right.
Similar to that, just like other dedicated modules like AES encryption and things like that.
Yeah, basically other specialized engines, if you will, or maybe platform components that used to be not on chip, like I/O engines, Ethernet controllers. What else? What else can you do if you were given 20 billion transistors or 10 billion transistors?
For the GPU, the 3Gs then.
That's right. You could put a GPU. That's like an accelerator, right? Some people call it accelerator, actually. Massively parallel accelerators. But yes, that's right. GPUs. Actually, that's already done. Actually, many of these are already done. But what else? Instead of replicating the core.
They've already tried making the cores larger, right?
That's right, yeah. But that's an alternative too, right? Making the core larger instead of replicating it. What else?
Add some FPGA kind of stuff which can be configured by
That's right, you could dedicate all those transistors to the reconfigurable logic and configure dynamically. We may cover that. That's one of my later slides. That's good. These are all good alternatives, right? Anything else? Should be better than the industry here, right? So following the industry, we can figure out what can be done better going into the future. No other options? Maybe you'll come up with some more as we look at some of these alternatives. So here is a very small list, if you will. And it covers some of the things that you've said. Except nobody said put more threads on the same core, I guess. That's an alternative too, right? So I'd like to cover some of these alternatives that people have actually considered before moving to multi-core. And some of these are already done anyway, but it's good to I'll take the approach of it's either multi-core, replicate the core, or do this. Obviously, you can do both, right? You could do a little bit of both. And that's what's usually done. But to understand the trade-offs, it's best to look at your alternative as another core versus this. Right? So that's the approach we'll take. Let's take a look at the first one, because that's what people were trying to do before they started putting more cores on the same chip, right? And more cores on the same chip, all of these are enabled by more transistors, higher integration. OK, that's the alternative, a bigger, more powerful single core. Now, what does it mean? You guys have taken 447 or 740, right? You can have a larger superscalar issue with. Instead of having 4 wide engines or 8 wide engines, have 32 wide engines, right? You can fetch 32 instructions at a time. Fetch, decode, execute, retire. Or you can have a larger instruction window. You guys remember instruction windows? Basically, you can buffer more instructions. Today, the most aggressive processors can buffer 128 or so instructions. What if we design the instruction window to buffer 4,000 instructions so that you can look ahead in the instruction stream and find independent instructions there? Well, you already know what the downsides of that are, but I'll ask you. You can have more execution units. You can have larger branch predictors, et cetera. Basically, things that would execute a single thread of execution faster, right? Single instruction stream faster. Because what is the advantage of this over multi-core? That's right. Improve single thread performance, right? And improve single thread performance without any changes, if you will, right? Nothing needs to change. The programmer or the compiler still behaves as they were behaving before. Right? And this is how the industry operated for a long time, at least the general purpose microprocessor industry. The assumption was the von Neumann architecture. You have a single thread of execution, and the hardware transparently improves the performance of that single thread. And on top of this, people have built software infrastructures, added more features into the software, which demanded more faster processors because now the software was slow. And people built faster processors this way. So it was this, I have this slide with this virtuous cycle, if you will. You get faster processors, people build more sophisticated software, more applications, still single-threaded, and that demands faster processors. But that cycle was broken because of what you will fill here, hopefully. So what are the downsides of this approach? Or is there another advantage to this? I don't know if there's another advantage to this. This is a huge advantage, though. Right? Because the programmer, arguably, the programmer is the most valuable resource, right? Because the entire software industry is much bigger than the hardware industry. And that's essentially, I mean, that's not the reason programmer is a valuable resource, but one could argue that programming is much more difficult if you actually take away the traditional way of doing programming from the programmer. So programmers are used to single-threaded programming. And if we take that away and replace it with something else like multicore, it becomes a lot more costly for everyone to improve the performance. Right? OK, so what is the downside of this approach then? Yes?
You simply can't get enough power into the processor.
Mm-hmm.
You hit like a power wall.
OK, so this, so I think if I rephrase what you're saying, doing all of this requires more power. And it becomes difficult to build such an engine because of power constraints. That's right. That's one of the reasons. What else?
You get diminishing returns with
That's right.
the benefit of use.
Yeah. So as you keep increasing the width, the size of the window, the size of your branch predictor, the performance benefits you get would be diminishing. In fact, we've seen this, right, many times in the previous courses. As you increase the width of your superscalar issue width, you get basically the curve you get is something like this. If I can find one of these things. On average, at least. This is your issue width. And this is your performance. Going from 1 to 2, you get a lot. And then you get some, and then you get some. But then you get diminishing returns at some point, on average, again. There are some applications that scale nicely, of course. OK, what else? Nothing else? Power and diminishing returns? How about complexity? I mean, this is difficult to design, right? Especially if you want to keep the performance while designing this. Because as you increase the size of your instruction window, what does that mean? That means you require a bigger register file, a bigger scheduling window where in an out-of-order engine, you need to pick the instructions. Remember, it's a restricted data flow engine. When an instruction executes, you broadcast a tag of that instruction, and all the dependent instructions capture that tag, become ready, and capture the value. Now, if you want to increase the size of your instruction window, that structure that does this tag matching and tag broadcast must be increased. And this is a big content-associative memory. And those are, first of all, complex to build and become harder to build if you want to keep a processor frequency, right? If you want to keep your frequency high. Why? Because now you need to broadcast. Well, if you look at this, this is what the structure looks like. Now I'm afraid if I put this up, something will happen. Let's see. What do you think? Should I turn off the display? Let's see. All right, display options. OK. Good. So far, so good. OK, so this is the instruction window. And well, reservation stations, where instructions wait until they become ready. And in reservation stations, you know that for each operand that we're waiting for an instruction, we have a ready bit, a tag, and a value. You can, of course, optimize this design, and people have tried to optimize this design with many, many different designs. But fundamentally, when an instruction executes, it broadcasts its tag and value. And this tag that's broadcast is compared to all of the tags of the instructions that are waiting. Right? And if you increase the size of these reservation stations, which you should do to get more performance, what happens is this tag broadcast bus becomes longer. So it becomes difficult to, and the delay of this logic will become limited by the delay of this interconnect. Right? And if you want to run at a higher frequency, then a bigger structure means that you will, at some point, not satisfy that frequency. You will need to pipeline the design. Once you pipeline design, now it becomes more complex because it's a critical part of the loop. Actually, I don't think I recommended this paper, but you can look at on pipelining dynamic instruction scheduling logic. Describes one way of pipelining the scheduling logic. I think this is Micro 2000. And it's by Jared Stark et al. If you're interested in some of the issues related to pipelining the scheduling logic, you can take a look at that. But there's no question that it becomes more complex. And this is just one part of the structure, right? This is the reservation station. What about the register file? Now you need to increase the size of the register file if you want. If you want to sustain 1,000 instructions in your machine, you probably want to have a large register file, right? Because they're going to write to registers. You can employ tricks to reduce the number of registers. You can quickly deallocate the registers that are not that are dead, for example. There have been proposals to identify that. You can release the registers that are known to be dead, meaning that are not going to be read by any instruction. But still, you need a big register file, which means that you need to have an engine that's more complicated, especially if you want to maintain the frequency. Okay? So complexity arguably is the most important reason why people didn't go this route, because these engines have been already very complex. If you look at the design of Intel Pentium 4, that's a very complicated machine. That's one of the most complicated out-of-order processors that was ever built, actually, perhaps. And if you want to increase the size of the instruction window that they had, which was 126 microoperations, you need to make it even more complicated, which not only complicates the design, but complicates the verification and validation as well. Okay? I guess I didn't cover this one, but we'll get to that. So basically, it's very difficult to design. And another way of putting it is designing at least efficient and simple ways of improving single-thread performance has become elusive. Right. And we already talked about power hungry. And why is it power hungry? Because these structures increase in size, right? This CAM increases in size, you need to do more comparisons at the same time. In fact, it becomes worse if you want to increase the size of the instruction window as well as the width of your machine, right? Your comparisons basically increase by, I guess if you call this issue width, oh, interesting. Issue width and instruction window, they stand for different things, but let's call this something else. This is your issue width, and this is your instructions. Basically, you get n-square complexity if you want to increase them by the same amount. Okay?
Why do you think that we need to keep the original design intact and increase the size of the buffers?
Yeah, we'll get to that. Yeah, that's another alternative, actually, no one has mentioned, which is basically design mechanisms that approximate the performance of this.
Maybe we have a new architecture.
That's right, yeah. But no one has come up with that yet. There have been proposals to simplify this, many, many proposals. In fact, if you look at their research and designs, as well as the designs, they incorporated some of these proposals. There have been many proposals to simplify this. But, and in fact, what I described here is not how things are implemented, because this is very, very inefficient. You implement the design with more simpler ways. But I'm not going into that right now. But still, it's difficult to design. Yes?
One of the factors which allowed us to do that was improvements in device technology. Transistors were getting smaller, and which means more faster and lesser power. So later it became stagnated. We couldn't go to a lower transistor device technology. That also contributed to.
But that contributes to everything, right? If your transistors are not becoming more energy efficient, it doesn't matter, right? Any substrate you build on top of it will be affected by that, basically. So that doesn't affect the trade-off that you make at an architecture level. You'll always want to have a more efficient design at the architecture level. Okay? Okay. Well, you already talked about this. And also, like traditionally scaling a single core with the traditional techniques that we have usually doesn't help, at least significantly, memory-bound application performance. So if your application is waiting for memory requests a lot, then either you need to scale to very large sizes of these buffers, or maybe there's another model where you can tolerate those latencies. Does that make sense? We covered this earlier in 447 and 740. Basically, if you get a load cache miss that takes, let's say, 1,000 cycles, and your issue with is 4 instructions per cycle, you need a 4,000 entry buffer to tolerate that. Right. But there may be simpler ways of actually tolerating this. Okay? Okay. So let's take a look at. So this is actually the way chip multiprocessors were motivated. This is one of the earliest papers on chip multiprocessors or multi-core processors that argued for multi-core. And their argument was essentially what we briefly talked about here. Maybe not briefly, but so they took 2 different designs. This is Neola Cotton from Stanford and his students. And this is the superscalar processor of its time, superscalar out of order. Basically, you have, I think it was a 6-issue, yeah, 6-wide engine. And they did some calculations. And with equal area, they evaluated the performance of this against this 4-core processor, if you will. It's a 4-core processor, and each of them was 2 wide. And they concluded that this is a better way to go. Well, I guess if you compare these two, what are the advantages and disadvantages? And when I say large superscalar, that should have been large superscalar out of order. It's basically this design. This is the argument in the paper, but this is also true. I guess I'll ask you the disadvantages. I'll give you the advantages. If you have multi-core, now you have simpler cores, right? Instead of this sophisticated machine, you have much simpler cores that are replicated. They're more power efficient, hopefully lower complexity, easier to design and replicate, and higher frequency because you have shorter wires. You don't need this very long wire. In fact, I think their processors were 2-wide in-order machines, whereas here you have 6-wide out-of-order machine. Okay? Also, applications, there are 2 benefits. One is the designer's benefit. The other is the application's benefit, right? You can have higher system throughput on multi-program workloads if you always have 4 cores, right? Especially if you have multiple applications that are important to you at the same time. And also, you can have higher system throughput in parallel applications. If you have multiple threads, you can run them on these different cores in parallel, whereas with a single thread out-of-order engine, you cannot do that, right? Now you can argue that you could actually add simultaneous multi-threading here, right? And we will get back to that again. And you can get some of the benefits, some of these 2 benefits with a large out-of-order engine as well, right? OK, so what are the disadvantages of multi-core? Yes? Say it again?
You have to maintain, like, all the processors have to see the same value that has stored. If the processor was modified that one, then all the processors know that value of the
That's right, yes, if you have shared memory.
Yeah.
That's true. But if you think of these processors, these 2 processors, as part of a larger system, then you need coherence here also, right? If this needs to go into a larger shared memory system, this chip still needs to support coherence. If this is the only part of your system you're right. This coherence is more of an issue here. But single-threaded processors actually need coherence also. Why? Because you have memory mapped I/O, and I/O, you need to keep the memory coherent. Yes?
It's just not going to be as fast on serial workloads. You can't look ahead as far.
That's right, exactly. Yeah, single-thread performance suffers with multi-core, right? Oh, there's more, I guess. Yes. Programmability. Yes. That's right. Now, you need to take advantage of the substrate, you need to have multiple tasks somehow. Either aggregate those tasks from different people, then in which case programmability may be easier. But if you have a single problem to solve, now you need to parallelize that. So it's worse for the programmer, right? What else? What other downside do you have with this? Well, you have shared resources between these different threads, right? Between these different cores, which means that you can actually degrade performance because of the resource contention that happens between these threads. Why? Because if you had the thread running entirely by itself, it would have all of those resources to itself. So its working set, for example, can fit into this cache. Whereas now, the working set of these threads may not fit into the one-chip L2 cache together. They could be thrashing all the time. Right. So you could actually get worse performance, even if you have more threads, in this case, because you have these shared resources. Or either shared or partitioned resources. It doesn't matter. You could get worse performance. OK, what else do I have? Well, I guess we talked about all of these, right? Yeah, single-thread performance obviously degrades. There's also the number of pins. Now you have potentially increased demand, right? Because you have more threads of execution. I guess this is another way of saying that there is more contention in resources. So there's more demand for memory bandwidth, which arguably is another very important resource that one should care about. And that's one of the, if you try to keep scaling the system, memory bandwidth, the number of pins you can put on chip will be a major limiter. OK? OK. So this paper actually argued in two ways why go for multi-core. One was a technology push that we've covered briefly. And they identified two things: instruction issue queue, or scheduling window. Size limits the cycle time of the superscalar out-of-order processor, which leads to even more diminishing performance. You get diminishing performance because you don't have enough parallelism in a single thread, potentially. But you also get diminishing performance because as you increase the size of the issue queue, you cannot clock the processor faster. Right? And you also get quadratic increase in complexity with issue width. This assumes that you increase your issue width as well as your instruction window size. And when you add large multi-ported register files, again, your frequency reduces, or you need to add more cycles to your pipeline, right? Again, which leads to diminishing performance. There's the other side that they looked at, which is the application pull. And they basically concluded that if you look at the floating point applications, this is SPEC. You guys are familiar with SPEC, right? Standard Performance Evaluation Corporation. They publish these benchmarks with which the systems are evaluated with today. And there's a particular benchmark that SPEC CPU that exercises just the CPU itself. And the floating point benchmarks are part of it. And these benchmarks usually have abundant loop level parallelism, meaning different iterations of a loop are independent. And you have different loops that are independent. So it's easy to parallelize these FP applications. You don't necessarily need a large core for that. That's not always true, because there are some there's some scientific code where you actually have big dependence chains. You may need a large core for that. The other conclusion here was that integer applications showed little parallelism, at least in the design they evaluated. I guess this has been a very ongoing debate in computer architecture for decades, if you will. How much parallelism can you extract from a single thread? What is the limit of instruction level parallelism, if you will? And usually the studies that are done have flaws. One of the reasons is when you look at the instruction level parallelism, people confuse the machine parallelism with actually what is extractable from the program. So, OK, if I tell you that I tried to figure out how many instructions I can execute in parallel in this program, let's say my program is PowerPoint. I took PowerPoint, ran it on a machine with 4 execution units, and I found out that the maximum instruction level parallelism that I can get is 1.2. Is that the maximum possible achievable instruction level parallelism that you can get from PowerPoint? What would you, no? What was the problem? The problem is you assumed a machine width of 4, right? What if you had a machine width of 1,000? So when you look at the instruction level parallelism in a single thread, you actually need to eliminate some of the bottlenecks. You can assume a branch predictor, for example, that's very inaccurate, or that's state of the art for its time, and then figure out what the parallelism that you can extract from the code is. And you may find that it's low. But that may not be the right conclusion, because somebody can come up with a better branch predictor, right, which would actually increase the instruction level parallelism. So the conclusion in this paper was little parallelism in integer applications, which may or may not be true. And I guess they also looked at some other applications, which is transaction processing and multiprogramming. In this case, they concluded that a multicore or chip multiprocessor is a better fit. And arguably, that's true, right? Again, if what you have is this, which is a single processor with a single thread, not multi-threaded, then these applications could be better fit. Or a CMP could be a better fit for these applications with many threads. Right? But now we'll examine the multi-threading engines also. OK. Any questions? And these arguments are actually the reasons that were also provided by the industry to move to the multicore, never explicitly provided. Power is, I mean, this part affects power, complexity, performance, and this part affects the pull of the applications. Applications are becoming more parallel, if you will. OK. I think we've covered, we've beaten that to death. So you hopefully know very well what the trade-offs are between single-threaded out-of-order engines and multi-core engines. But I'd like to ask you a question. So this was the comparison that was made in this paper. This was the 6-way superscalar out-of-order processor. And this was the multi-core processor, 2-way. Basically, issue width was 2. And you had 4 of them. And this is the this is a processor model that was evaluated for both of these systems. Do you see something not so great here? I'm not suggesting this would change the conclusion significantly. But there's a reason that I put this up, because this is something you should avoid in your evaluations in general.
6 and 8.
OK. I think you're pointing out the degree of number of instructions. Basically, here you can fetch a 6. Here you can fetch 8. Yeah, that could be one of those things. But maybe the argument in the paper is that these are simpler cores. So you can actually put more of those together and fetch more instructions per cycle. And that argument you could probably buy, right? There's some other thing. I don't know if people can see this. You want me to zoom into it? If I can. Say it again. L1 in time. Where is that? So it's 2 cycles, and it's 1 cycle here. That's interesting. I never looked at that. So why could that be? I guess we could reason back and say it again.
The cache is smaller. That's where it has.
Oh, that's right. Yeah, maybe here they had a bigger cache. Here they had smaller caches, so they partitioned the cache. So that makes sense also. What else? What I'm looking for could, yeah, go ahead.
This four-way, the four processor system has 4 times the number of registers.
4 processor system has, but the total number of registers is still the same, right?
Oh,
The physical registers is still the same. Okay. The architecture registers has to be 4 times because you're actually executing 4 threads. But what I'm looking, yes. That's right. Yeah, I don't know if they model the contention, but you may be right. Actually, that's a good point. I wasn't thinking of that. I don't know if that contention is modeled. You're right. Hopefully, this may be the uncontended latency. So, yes.
They have L1 cache leaving, so for memory is like a big holdup. That's the bottleneck. This superscale processor connects to 8 load store ports, whereas each single individual processor has
I see. So here we have 8 banks, which means that you can I guess it's an advantage for the superscalar processor, right? That's true, yeah. Yeah, I don't know why that was not. It's good. You guys are coming up with things that I didn't think about, or I had thought about, but that was a long time ago. There's some. What I'm looking for is related to integer performance, actually, or balanced design. Remember from my courses, what is a balanced design? Yes.
Reduce your width is much larger than the number of integer functional units you actually have.
That's right, yes. That's very important, especially if your conclusion is going to be integer applications are not going to gain that much from an out-of-order execution engine, right? A larger superscale out-of-order execution engine. So if you look at this, the width of the superscalar engine is 6, and the number of integer functional units is 3. Now, one could argue that this is not a balanced design, right? Because if you're spending the resources to actually build a 6-byte superscalar engine, it's not as hard to add 3 more functional units and schedule instructions. It's a little bit harder because, yes, you need to schedule those, but it's still doable. Now, to the credit of this evaluation, there's the 2-byte core in the multi-core engine also has a 1 execution unit. Arguably, this makes even less sense. It's easier to put 2 execution units here, right? Why would you want to design a 2-byte machine with a single integer execution unit, right? OK, so these are, I mean, this may not change the overall conclusions that happen, but these are the kinds of pitfalls you should really avoid when you're doing your projects, for example, or when you're doing research. And this may not change the importance of the paper or anything significantly, but it may also. OK, so I would argue that these are not balanced designs, at least in terms of the number of instructions they can execute, versus how many instructions they can fetch. OK, I think we'll see some things, some similar things later on. OK. The other alternative, one of you guys suggested, is bigger caches, right? Let's take a look at that. Why not, instead of putting more cores, why not put more cache? Cache will what?
Become slower.
Cache will become slower. OK, you started with the disadvantages.
Oh.
That's true. I guess I didn't ask the right question, that's why. Yeah, will become slower. If you increase the size of the cache, it will become slower, right? Well, then I'll say that why not put more cache in a reasonable way as a hierarchy? You could still have more cache and still get the benefits, right? That's the memory hierarchy. And you will say that your design becomes more complicated, right? As you add more levels into the hierarchy, it becomes more complicated. Plus, what is another downside of adding more cache?
How does it help data dependency? Doesn't have a dependency on instruction. It will only help this, like you have to go to.
That's right. It'll help if you have a good memory locality. That's right. It doesn't help with computation dependencies if you don't go to memory. I think what you're getting at is a cache may not always be helpful. Right? And that's true. Even with memory intensive applications, it may not always be helpful if you don't have locality. Right? If you don't. Yes?
Yeah, it's just generalized. I say you can't, you won't necessarily get rid of cache misses just by increasing the size of the cache.
Yeah, that's right. Not all of them.
Yeah, not all.
You will get rid of some of them, hopefully. Yes?
As you make your cache bigger, you have to make sure that your TLB actually
I guess that's true, yeah. You need to, because otherwise your TLB will be bottleneck. You'll be missing your TLB. Yeah. But TLB is also a cache, so that covers my statement. It's a bigger cache. You basically need to increase the size of your caches everywhere. But you're right. You're absolutely right. Okay. So those are disadvantages. What about the advantage? There must be some advantage to this, right? Compared to adding more cores. Yes?
Hopefully has fewer cache misses, right?
That's right, yes. That's right. And also it's arguably simpler, right? If you don't need to, well, I guess this part is true, right? Again, this is a transparent technique. It improves single thread performance transparently, assuming it actually does. And it's simple to design, right? But multiple levels complicate the memory hierarchy. And also you get diminishing single thread performance returns, as we discussed. Because, and in fact, some threads do not even benefit. OK. I guess I'll show you a cartoon of this. There's another way of looking at the problem. Adding more cache is somewhat embarrassing, right? So if you look at the evolution, this is just a cartoon. Don't take it with a grain of salt. Evolution of microprocessors and cache. This is the beginning of time, if you will. Initially, we had no cache on the microprocessor, right? It was 0. And then we started putting some cache on the chip. And then microprocessor started growing, but caches started growing a lot faster, like big caches, megabytes of caches. At some point, it became so ridiculous that the entire chip, which is supposed to be executing, doing computation, right? That's why it's called a processor, processing. Entire chip started becoming dedicated to data transfer or storage, which is cache, which is what a cache is. So because this was embarrassing, computer architects started putting more cores, eating away the cache space. And that's how things evolved. That's true, yes. That's why you need to increase both. Assuming you have good locality, or you could exploit that cache. Yeah, but this is taken with a grain of salt. But this is, if you don't take the story around it, this is pretty much what happened in the industry. And some systems have huge caches today. If you look at IBM, I guess what they have today right now is Z-Next, right? It has huge amount of caches. I think they have an Z196 had an L4 cache of 192 megabytes, I think, if I remember correctly. Now, it's not on chip, so that part is it's a separate chip. Actually, I think it's 2 chips put together. But the on-chip cache is it 32 megabytes? Anybody remember? Nobody studies the Z architecture. Those are interesting chips. So. OK. I guess let's take a look at another alternative. Again, instead of replicating the core, why not add more threads that get multiplexed on the same single core? And you could do this in multiple ways, as we briefly discussed. And we will cover this in much more detail in a later lecture. You could do fine-grained multi-threading. You could basically fetch from a different thread every cycle. That's, let's ignore that for now. Let's be more aggressive. Let's try to execute instructions from multiple threads at the same time, which is simultaneous multi-threading. This way, you can have an out-of-order execution engine. And the functional units, you can have many functional units. And they could be utilized by different threads at the same time. So now it's looking like you would get the benefits of multi-core, right? You can execute multiple threads at the same time on the same hardware. In fact, it's more finer grained than multi-core. You don't partition the processors. You can share the resources of a large out-of-order engine across different threads. So what is the advantage of this? No advantage over multi-core.
You get better utilization of the functional units?
That's right. You will have better utilization of the functional units, right? Because you don't partition your functional units. In a multi-core engine, different threads executing on different cores cannot use the functional units of another core. Whereas here, all of the threads are executing on the same core. Well, I guess I didn't have it, huh? OK, I was hoping to get to your point, but we should add this point. Han. That's actually an important point. I guess this kind of gets into that. But you basically exploit thread-level parallelism just like multi-core. And you also get good single-thread performance, right? If you have SMT, and if all you have is a single thread, you just execute it in that out-of-order engine instead of going to a smaller core. Right? And there's no need to have an entire core for another thread. And this also improves parallel performance compared to multi-core, because now you have cache sharing at the very low level, right? The data cache is shared between different threads. So one thread can write to the data cache, and another thread can right away read from it. And you don't need coherence, if you will, between these threads. OK? I guess I've given you all of this. But I don't want to keep you here until tonight, so we can go a little bit faster. Unless you want to be here. OK. So these are the advantages. Actually, these are pretty compelling advantages, right? You get good single-thread performance and good multi-thread performance. You get better functional unit utilization. You don't partition resources. And you get potentially better parallel performance.
We could argue on the last point that if we don't really need the data sharing, one thread will kick out the cacheness of other.
OK, so now you're going into this part. That's right, yes. So this is a double-edged sword, right? Now you're contending at the lowest level, if you will, of the hierarchy, which is the data cache. And if the two threads are thrashing each other in the data cache, you can get worse performance than multi-core. So I guess because your resources are not partitioned, as in multi-core, you can get worse performance for each thread. What else? There must be some other disadvantages. Yes?
So maybe not always easy for compiler to extract fine-grained parallelism in code.
That's true, but that's true for multi-core as well, right?
All right.
Yeah. We're comparing to multi-core, remember? Yeah, the programmability issue remains in both when you need to execute multiple threads. What else? Yes?
Is there like operating system overhead related to maintaining all these threads?
That's true for multi-core also, right? If you do an apples-to-apples comparison, 4 threads on a single core versus 4 threads on 4 cores is no different in terms of the context you need to maintain. Okay, I won't keep you. So scalability is an issue in this case, right? It's not, this approach is not as scalable as multi-core. It's because you're sharing resources and you're actually multiplexing different threads, executing them together on the same out-of-order engine. If you want to add more threads, now you need to increase your register file size again, right? You need to increase your issue queue size. Or you need to increase the issue width to have many threads, right? Because it makes no sense to have 4 execution units and 100 threads on the same core. That will be your bottleneck. Right. So you need to build an engine with 100 execution units, let's say, and also 100 threads. And that is difficult to scale. Because essentially you're building a large out-of-order engine in that case. Okay, so this becomes more complex with more threads. And in fact, we will see papers, we will read papers later on when we cover multi-threading that actually show that you get diminishing returns. If you even if you increase the size of your register files in a reasonable way, you get diminishing returns as you add more threads on a large out-of-order engine. I think Intel has reported results. They have simultaneous multi-threading in many of their machines right now, right? That's right. I don't think they call it simultaneous multi-threading, but it used to be called hyper-threading. I don't know what's called today. But they report results showing that you get around 20 to 30% higher performance if you add one more thread. And after that, you get diminishing returns. OK. I guess shared resources in general limit the performance of parallel performance, so shared fetch bandwidth. In multi-core, you can make the fetch engines partitioned, right? So you could actually fetch from multiple threads at the same time in parallel because you have independent fetch engines. Now, you need to design your processor such that it can, let's do a comparison with a multi-core that fetches 2 instructions per core and 4 cores. That's 8 instructions per cycle. If you want to design a single core processor that can fetch 8 instructions per cycle, that's harder. Why? Because you need to have a good branch predictor. Right? You need to, there are fetch breaks that you need to handle. If there's a taken branch, what do you do? How do you fetch from that next location? OK. And you get extensive resource sharing with simultaneous multi-threading at the pipeline and the memory system level. Your data cache is shared, your pipeline is shared. So if one thread is actually demanding a lot more than others, now you could lose performance. This affects both single thread as well as parallel application performance, right? Now you could control some of this sharing. You could partition the resources, and that starts looking more like multi-core now, right? So this is actually a fluid spectrum, even though we're treating it as this versus that. You could have we're looking at 2 ends of the spectrum, multi-core versus multi-threaded. You can actually have something fluid in between, right? Something partitionable. And we'll look at that. Any questions on this? So this alternative we'll cover a lot more in detail when we talk about multi-threading. OK. I guess one other alternative that you guys mentioned, a more general form of it is you could integrate platform components or accelerators, if you will, instead of having more cores. Right. Why not do this? Or why do this, first of all? Let's start with the positive side. Yes?
There are certain things that happen a lot, like with business machines. They may need a lot of encryption. And so if it's a feature that gets used a lot, doing it in the hardware is a lot better than doing it in the software. Having to go through like one, you should use super optimized for those specific operations. So if you use it a lot, then it's valuable. But if you don't use it, it's just wasted data space.
That's right. So you covered both the advantages and disadvantages, I guess. That's right. Basically, you could accelerate. You could get significant performance benefits by integrating more components on the same chip. And this could be either hardware components that used to reside off chip or software components that happen to be executed a lot, right? You could design accelerators. You could put the I/O controllers on chip. You could put the encryption, decryption engines on the chip. You could put the graphics units on the chip, right? That's essentially that used to be a platform component. And if you put it on chip, that's another way of utilizing those transistors. And you could speed up many functions, right? Well, memory controller is another example, right? Memory controllers did not used to be on the same die as the processor. Now they are all on the same die. Yeah, you could speed up many system functions, basically. And arguably, these are perhaps the most important because almost all applications use the memory at some point. In terms of, these are most important in terms of integrating on the same chip. And these were one of the first components that actually got into the chip processor die. OK, the downside is, yes, as Joel mentioned, what if these are not used, right? It's kind of similar to multicore. If your cores are not used, you're wasting space. Again, here, not all applications benefit, right? If you have CPU-intensive code sections, multicore benefits them because you can execute multiple threads, assuming you can parallelize again. But here, these are relatively specialized except for the memory controller. OK? Any other downsides, upsides? Yes?
Upside,
Yeah.
you can reduce power consumption by moving the stuff much closer to the cores.
That's true.
Uses less energy to communicate a shorter distance.
That's true. Exactly, yes. You could actually reduce energy and power consumption also. So that's a good thing to add. I need to update these slides. But that's the purpose of these slides, to start this discussion. Yeah, integrating more components actually improves your energy efficiency also. What else? Yes?
Form factor.
That's right. You become smaller, right? Absolutely. You don't need to have multiple chips anymore. In fact, the picture we've seen at CM5 was you have 5 chips, if you remember. Now you can put all of that on the same chip. You had the Spark processor, you had the vector units, you had the input and output packet processors, and the memory. I guess memory may be a little bit difficult. Although even that you can embed, right? At least that size of memory. Remember, they had 32 megabyte memory. Now we can put 32 megabyte, well, SRAM even, on the same chip. That's right. What else? OK, I'll let you think about it. Let me know if you find anything else. So let's make it a little bit harder. We looked at a bigger, larger core, right? But that's not the best way to scale up single-thread performance, right? Why not have a more scalable, bigger core? More scalable, superscalar, out-of-order execution engine. And you guys hopefully remember some of this, right? We covered this somewhat in 447, but in more detail in 740. Do you remember the clustered superscalar processors? No? OK, I'll remind you. And you can have multiple threads executing on these clusters as well. So the basic idea is this. Instead of when you're scaling up your instruction window and register file, don't do the dumb thing, if you will, which is scale up a monolithic structure, but basically cluster it. So this is the well, I guess we'll do this. So you have your instruction window and your register file. I don't know how to make these big. I guess I do. Instead of doing this, just do this. And hopefully these are and cluster your execution units too, right? This is your register file 0, register file 1, register file 2, register file 3. And this is your instruction window 0, 1, 2, 3. Or scheduling window, let's call it. This is the reservation stations. Make sense? And this is more scalable, right? What you can do is when the instructions come in, you steer the instructions to an appropriate reservation station. And those instructions execute in that reservation station. In fact, these could be FIFOs, right? What does that mean? You could have basically the only instruction that you can schedule is the oldest instruction that you put into these queues, assuming these are FIFOs. Let's say you fetch a load, you've put the load here. You put the dependent instruction add here such that they can communicate within the cluster. But if you get an independent instruction, let's say multiply, that is not dependent on this add or load, you can put it here. So basically, this is called dependence-based steering into these clusters. Basically, check which cluster the sources of that particular instruction will be produced and place that incoming instruction, the fetched instruction, into the cluster where it will get, where its sources will be produced. Right? That way, you can put dependence chains into different clusters, which means that the hope is that they will not be dependent on each other, and you can execute them independently. Right? Does that make sense? And the scheduler is very simple. It basically checks whether the head of the queue is ready. The instruction at the head of the queue is ready. Now, what does that mean? That means that when you execute an instruction here, you broadcast the results not to the entire instruction window, but just to the head of these queues. So it's much more scalable, at least the broadcast part. Right? And you can still get the benefits of out-of-order execution because you could actually schedule all of these let's say all of these 4 instructions at the head can be ready, and they can execute in parallel. Right? And these are not necessarily in order, because you're actually putting instructions into these queues based on their dependencies. Make sense? So that's the idea of clustering. I guess I'll quickly skip over this so that you don't see it. But I anticipated that we didn't necessarily cover this. But this was actually employed first in Alpha 21.264 integer units. What they had was, well, they didn't have the FIFO queues, but they partitioned the register file. And they steered instructions. Well, they didn't partition the register file. They had 2 copies of the register file. And they could steer instructions to 2 separate instruction windows. And the reason was they had a 4-byte engine, 4-byte execution engine, which means that they needed 4 times 2, 8 register read ports. And they wanted a high-frequency machine. I think it was at the time 500 megahertz. And they couldn't design the register file to operate at that speed in a single cycle if the register file required 8 read ports. So what they did was they basically clustered the machine. So they had the instruction window 0 here, instruction window 1 here, and they were able to schedule 2 instructions here and 2 instructions here, which means that each register file now required 4 read ports instead of 8 read ports, right? So you can build your machine to be more scalable that way. And this was actually employed in Alpha 21-64. I think you read that paper, right? If you've taken 740. No? If you haven't read it, this is a very nice paper. It's by Kessler. I think the Alpha 21-64 microprocessor. This was the fastest processor of its time. I think it's IEEE Micro. Can't remember if it's 97 or 99. But hopefully you can figure it out. But that's basically the idea of clustering. You simplify this core. Divide the scheduling window and register file into multiple clusters. Steer the instructions into clusters, for example, based on dependence. You could imagine many other ways of doing this, right? The compiler can specify which cluster instructions goes to.
You can't find out all the dependence before the instructions are executed. You make it simple small. Or you may have to be extra.
Okay. How can you not find out the dependencies?
The addresses, for example.
That's right. So this doesn't work with memory very well. You need to predict where the memory goes. That's right. So that we haven't handled very well. Yeah, what do you do with the memory operations? That's usually a less scalable part. But we'll get back to what you said, because actually you cannot even find out the register dependencies, right? And we'll get to that. So clusters schedule instructions out of order. Across the clusters, you can do out of order scheduling because they can slip compared to each other. But within cluster scheduling can be in order, just like this, FIFO. And inter-cluster communication happens via register files. This is register communication. And what they did here was, in alpha, when an instruction, these registers were actually replicated. So they didn't partition the register file physically. So they just replicated it. If you had an instruction, let's say add, that wrote to register 1, this register 1 was communicated to the other register file after 1 cycle. So the value would be available right away here and 1 cycle later in this register file.
That returns the bit code.
Say it again?
It returns the bit code and write code. Where is that?
I couldn't hear.
To communicate the values in the register file from the copy, you need to read it and then write it. That returns your bit codes.
But you don't need to read it, right? You need to write it. You need a write port. No, it's already written, right? If you have an instruction add that writes to R1, R1 is already being produced. So you write it here and also write it here at the same time. So you don't need to read it from anywhere. Okay? So that communication also happens. So if you partition the register file, actually you have another issue. So you don't know the dependencies that you said. Let's say an instruction sources 2 registers. Its dependence may be in 2 different clusters, right? Which means that you don't know where to put that instruction. Well, you put it in 1 cluster, but then the other value needs to be communicated. So that's the downside of clustering, if you will. Your latency increases if you need to communicate between clusters, right? Let's say you had an add instruction coming in, and this multiply and this other multiply was producing values. This is multiply into R2, multiply into R3. And add was taking R2 and R3. Let's say you steered this add here. And this multiply executed first. You get the result. And you need to wait for this multiply. But there's extra delay because this multiply is in a different cluster. Right? So that reduces performance compared to this monolithic engine. Okay? So the advantages are smaller windows, simpler wake-up algorithms, hopefully, smaller ports or fewer ports into register files, and maybe faster within-cluster bypass, but then extra delay when instructions require communication across the clusters. And this is for your benefit, I think. This is one way of looking at the clustered machine. You have different scheduling windows, different register files, functional units. These are fast bypass. And across cluster, you have slow bypass. Bypass is the same as forwarding of the data. And this is a picture from another paper you should probably read. I guess I'm running out of space on it. So clustering was, I guess I'll put it into your instruction window here. This is Palacharla et al. It's called Complexity Effective Superscalar Processors. This is from ISCA 1997. So what they did was they analyzed the complexity in terms of latency and critical path you would have if you increase the size of your instruction window, scheduling window, and the width of your issue width. They, in all pipeline stages in a superscalar processor. And they found out that the limiting paths are actually this broadcast as well as the bypass of the results from one functional unit to another functional unit. As you increase your issue width, as well as instruction window, those paths become the critical path. And to alleviate that, they actually proposed the clustered architectures. And this was their proposal. Well, this is the original superscalar engine. And the analysis in this paper is actually very interesting. It's more circuit level, but I would encourage you to go and look at it. There are a lot of insights to be taken from it. So basically, their proposal was essentially what I drew here. Instead of having a large window here, have a steering logic that steers into FIFOs instead of having the large monolithic window, I should say. And you basically schedule out of these FIFOs. And only consider the head of the FIFOs. Okay? Oh, I guess you have the thing here. Basically, when you make each of your schedulers FIFOs, now you are simple, right? And maybe you can have even more FIFOs. You can think of it that way too, right? Maybe you can actually make it more scalable than this monolithic window. Because all you're doing is really examining the head of this FIFO. And you can still have out-of-order execution. This reduces scheduling complexity. But this could also lead to more stalls, right? If you don't put your instructions carefully here, I guess there are several issues here. One is the communication. You may put a dependent instruction to some other FIFO. And the second is, whenever you have something like this resembles very much what we saw in the first class, right? Remember the parallel task assignment? Now we're assigning instructions here. You can get load imbalance here, right? If all instructions are dependent on each other, you'll have load imbalance here. And then you'll be filling the other ones. So it's hard to balance the load in the presence of dependencies. OK, and this is another way of looking at it. This is their, well, I guess this shows the bypass here, basically. I say here, results produced by a functional unit in cluster 0 are not individually forwarded to each functional unit in another cluster. So that's why you get the additional latency. So when an instruction here executes, its value is not immediately available. The reason it's not immediately available is you don't have full connections between these functional units. If you had the full connections, then it would be looking more like this. It will be more complex, right? And these are essentially, you could think of these as crossbars, right? If you allow communication between every functional unit to every other, it's like a crossbar. And that limits the scalability of a large machine with a large issue width. Okay? You cluster it, you cut the communication. Now the problem is if you need to communicate between the cluster, that takes longer.
Keep one functional unit with the communication.
Say it again?
Keep one functional units with the communication.
I couldn't hear.
So here the clusters are totally separate, but we can keep one functional units which bypasses the values for other functional units. So instead of totally two separate clusters, there could be some communication. So you don't bypass to each and every function.
I see. Yeah, I mean, you could do that. You could increase the connectivity a little bit more, but that's, yeah, then your design becomes harder.
But you
Right.
know which one is the equipment and you can configure it.
Well, you need to schedule your instructions with those functional units that have the connections then. And that becomes a scheduling problem. And that makes something else harder in the machine. Right? Yes?
So in this design, to reduce, since the bypass network was they were to make, they tried to reduce the complexity there and put that logic in the steering logic in the front side, and then try to like balance the pipeline.
Yeah, you could say that the complexity is moved to the steering logic. That's right. And you're right, because the performance of these machines very much depends on how good you do steering. Sometimes it's just tough to do steering, depending on your dependencies in your program. Okay. And because of that, actually, the performance reduces if you don't do good steering and if you have a lot of inter-cluster communication. And you also have limited out-of-orderness, right? Like an instruction here may actually become ready. Let's say all of your queues are full. They have some, not full, but they have some things here. And the head instructions at the head are all waiting for some value. You steer an instruction that's independent of everything else, well, too bad, it cannot be scheduled because these are FIFOs, right? So it's not full out-of-order execution. That's where you lose the performance. In fact, they evaluated the performance of this design, and they found out that the performance improvement compared to this design lost approximately 20% performance compared to a monolithic engine of the same size. So 20% is actually a lot of performance. Okay. Okay, that's a big diversion to clustering, but this is important. So now we can go back and look at why this is good or bad. So why is this good compared to, well, I think I should say one more thing. You could make this multi-threaded also, right? You could easily have multiple threads and have a mode where only one thread uses this cluster, another thread uses this cluster, another thread uses this cluster. You could also partition it in different ways. You could have two threads and they both use these two clusters. Well, one thread uses these two clusters, another thread uses these two clusters. So in that sense, it's a little bit more scalable also. So what is the advantage of this compared to having another core, or multi-core? None? Well, I guess this is not compared to multi-core, but that's okay. It's simpler to design this than a just regular superscalar out-of-order engine, right? You're not, I should say monolithic actually, a monolithic superscalar out-of-order engine. It's also more scalable than simultaneous multi-threading. You could imagine adding more clusters and more threads because you're kind of partitioning the clusters. And compared to multi-core, you can improve single-thread performance and parallel application performance at the same time. What is the downside? That's right. Yes. Basically, you have diminishing performance returns on a single thread because the steering becomes difficult. And as you simplify the schedulers, you lose performance because now your out of orderness reduces. Okay, we've already talked about this. And parallel performance, if you have multi-threading actually, again, you're still limited by the shared fetch bank. Now you could argue that you could make this fetch unit separate also here, but then now it's looking like multi-core. But that's something you guys should think about also. Maybe multi-core, or these separate multi-cores is not the best way to design systems. Maybe you actually have a pool of resources that you can either dynamically partition or operate together. And we may look into that also. If you had these fetch units and register files and these schedulers, maybe you can mix and match, if you will, for different threads. If you had one thread, enable all of them for the same thread. If you have 4 threads, partition them between 4 threads. If you can do that, that would be a design that's, I guess you could not classify it as multi-core, you could not classify it as clustered, but it's something else. Okay. And I guess I'll add this. A clustered superscalar processor, while it's easier to design than a monolithic superscalar out-of-order processor, it's still difficult to design. It's not as easy as stamping out cores, if you will. Because you need to figure out that steering logic. You need to figure out what happens when you need to transfer operands. And especially if you want to get good performance. Okay. So we covered clustering too. Okay, another alternative. There are many alternatives to multi-core. Why even do multi-core? I mean, we're not putting more components on chip. Why increase the size of these chips? Why not just have a single core and have traditional multiprocessors? I guess this says that don't put more transistors on the same chip. That's an alternative too, right? Or at least don't use those transistors as multiple cores.
So you're saying make many small dies effectively?
That's right, yes. Make many small dies effectively. Why not do that?
Well,
Yes.
I was just saying the clear disadvantage is that there's the latency of communication between going off chip is much slower than on chip communication.
That's right. So your parallel performance is worse if the threads are communicating. If you put those threads on cores that are on the same chip that are sharing caches, the latency is much lower, bandwidth is much higher. So both, you gain on both. And that's the clear disadvantage, you're right.
Overall area consumed will be more. If they are putting everything on the same platform, it's more compact to have things on the same chip. And effectively the cost will also reduce.
That's right, that's very likely. Area is reduced because now you can put more of the cores. There are 2 reasons, I think. One is you get rid of these chips and pins. And the second is you can share resources much more easily if you put things on the same chip. What is the advantage of this though? No advantage? There must be. There we go, smaller die size, right? There are advantages to it actually. You can, yeah, exactly. You can get that, and also you can get. It's likely that you'll get less faults, and this is for the same processing parties. And you can have more memory bandwidth, right? Because now your pins are not shared. And that could be. Well, at some point you will be shared. That's right. But you can design your system around that also. Whereas if you put multiple cores on the same chip, you're just shared and you're stuck with it. Those pins are shared, right? Whereas if your pins are not shared, going out of the chip, you can design the rest of your system such that it's less shared. At some point, your memory will be shared. That's right, if you want to improve your resource efficiency. And that will be the bottleneck. Okay. I guess the other advantage is, yes, you have fewer shared resources, right? So there is an advantage to this design point too. Well, less contention between threads. They contend at some point down in the hierarchy, but not on the same chip. But the downside is obvious, and this is actually one of the big reasons multicore or having multiple threads on the same chip is important, that communication latency and communication bandwidth. You just cannot get that kind of latency and bandwidth if you're communicating off-chip. So your parallel application scalability is very, very limited if you don't have multiple contexts on the same chip. And because you're constrained by less sharing. I guess there's no reason you cannot share the caches if you have different chips, right? You could design your system, entire system that way, such that you could share some other chip's cache. But again, the problem is the latency to access that cache. So you could do that, but you still have less sharing. Okay. Any questions? Any more upsides, downsides on this? But there is an interesting balance because of some of these bottlenecks. How many cores do you put on a chip? At some point, you'll be pin bandwidth limited. It may make sense to limit the number of cores you put on chip. Okay, other alternatives that we will not go into as much detail, at least right now, some of you have suggested, like more vector processing. Right? This is kind of done with the GPUs right now, but you could think about the advantages and disadvantages just like we did. Or data flow is another interesting alternative, right? I guess these are some of the alternatives that the industry didn't consider that seriously at that time when they made the movement. Some of these are, a lot of these are actually considered implicitly or explicitly. But these are less so because, well, data flow is not, because there is no data flow processor that exists even with us, even at that time, right? A working one. And this is known not to be not flexible. And this is known to be not possible, almost, with significant downside. Without significant downsides, it's not possible, right? Integrating DRAM on the logic process. It makes the, basically these are two different processes that increase your cost significantly. And reconfigurable logic is another one, except if we can use it, right? But these are all important directions to examine still. And you could think of, maybe except for the third one, you could think of accelerators placed on the chip that aid multiple cores, right? You could have a SIMD accelerator, which is what a GPU is. You could have reconfigurable logic as an accelerator. Maybe you could have a data flow engine also at some scale. Okay. I was hoping to cover much more than this, but this is kind of a picture of what we've covered, if you will. These are some of the alternatives to multi-core that we've covered in some more detail than these other ones. And I'd encourage you to think about other alternatives also, or maybe enabling some of these alternatives in different ways. Of course, today's systems do many of these things together, right? They maybe not the bigger, more powerful single core that has come down for a while. That's why the single thread performance is not improving as fast. But today's systems have bigger caches. They have multi-threading. They did integrate platform components. They did try to make the superscale out-of-order engines much more scalable. Well, I guess this exists anyway, regardless, but not at the expense of having more cores. And there's also vector processors on chip as well. Okay. But it's always a good idea to think about other alternatives, alternative execution models, where you can get much better performance and much better efficiency. And I would encourage you to do that. If you have project ideas related to that, I'd be happy to listen. So I guess let's stop here, unless you guys have questions. Then we'll delve more into multicore next time. Okay.